Welcome students to the video module on photoelectric emission. Before learning the topic photoelectric emission, we must check what is meant by work function of a metal. We know that a metal consists of large number of free electrons. These free electrons can move on the surface and inside the material, but we cannot make these electrons to come out of the metals. It is bound to the nucleus with some sort of energy. So we have to supply that much energy into the material in order to eject these electrons. So the minimum amount of energy required to eject an electron from the surface of a metal is known as the work function of that metal. The minimum amount of energy required to eject an electron from the surface of a metal is known as the work function of the metal. Work function is different for different materials. It is least for cesium and it is maximum for platinum. Work function is normally represented by the symbol 50, or is also W also used for that. Okay. So for ejecting an electron from the surface of a metal, this much minimum energy we have to supply. But how can we supply the energy to the surface of the metal? There are three different methods by which we can supply this energy to the metal. One is known as thermionic emission. Second one, field emission. Third one, photoelectric emission. In thermionic emission, the energy required will be supplied by providing in the form of heat energy. That is why the name thermionic emission. In field emission, a high electric field is applied for ejecting the electron from the surface of the metal. And in photoelectric emission, light of sufficient frequency is allowed to fall on the surface of the metal to eject the electrons from this. So these are the three methods for providing energy to the metal. Once again, work function is the minimum amount of energy required to eject an electron from the surface of the metal. This minimum energy we can provide either by means of thermionic emission or field emission or photoelectric emission. As I told, photoelectric effect is the phenomenon of ejection of an electron from the surface of a metal when light of sufficient energy falls on it. Sufficient energy means the energy must be equal to or greater than the work function of the metal. Okay. So when an electromagnetic radiation of sufficient high frequency is incident on certain metals like sodium, copper, cesium, etc., electrons are emitted from them. This phenomenon is known as photoelectric emission, and the emitted electrons are known as photoelectrons. Photoelectric effect is first observed by Hertz in the year 1887. We can see the experimental setup for studying photoelectric effect. You can see the experiment setup here. It consists of an evacuated glass tube with two metal plates. One plate is negatively charged and the other one is positively charged. And the plate connected to negative is a metal with lower value of work function, such as cesium or any such material. There is a quartz window attached to the glass tube for allowing electromagnetic radiation to fall on the metal plate, and the potential applied to the positive plate can be varied. When no light falls on the metal plate, the ammeter shows 0 reading. But when light of sufficient frequency fall on it, ammeter shows reading, indicating the flow of current through the circuit. So when no light fall on it, there is you know that there is a gap between the two electrodes, so that there is no current there is no current through the circuit. So that is why the ammeter showed 0. But when light falls on it, then the ammeter showed reading. That means a continuous supply of current occurred there. So when electromagnetic radiation falls on the metal plate, photoelectrons are emitted, and we know that electrons are negatively charged particles. So this plate is a negative plate, this is a negative plate, and this one is a positive plate. So electrons are accelerated towards the positive plate, and it completes the circuit. That is why when electromagnetic radiations of sufficient energy fall on it, the ammeter shows a reading. Now there are few observations based on these experiments. So what we saw now is electromagnetic radiations fall on the metal plate, photoelectrons are emitted, and these emitted photoelectrons are accelerated towards the positive plate and completes the circuit and causes a current, and that current is known as photoelectric current. Now there are few experimental observations. The first observation you can see in this graph. It is a graph between intensity of incident radiation and the photo current generated. We can see that as the intensity of incident radiation increases, photoelectric current also increased. Remember, we are changing intensity, we are not changing frequency. For example, red light is incident on it. Red light has got a fixed frequency, but we are changing the intensity. Or we are using yellow light, then we are changing the intensity. Okay, so we are not changing the color, we are not changing the frequency. Instead, we are increasing the frequency. So what they observed is that on increasing the intensity of light, photoelectric current also increased. That is the first observation based on this experiment. Okay. In the next experiment setup, we can see that the positive plate potential. So by making the intensity constant, they increased the positive plate potential. So on increasing the positive plate potential, you can see here in this graph, the photoelectric current slightly increased, then it maintained a constant value. So on increasing the positive plate potential, photoelectric current increased slightly, then remains constant. Now on reversing the potential, that is positive is applied to the plate C and negative is applied to plate A. So as negative is applied to plate A, these electrons are also negative charges. So the plate A is now opposing the movement of electrons. Therefore, the speed of electrons reduces. Therefore, the photo current reduces. That we can see in the graph here. So this is actually a combination. This is actually a graph for 3 different frequencies. Consider only one frequency, nu1, which is shown here first. So you can see that the photocurrent reduces as the retarding potential increases. We know that retarding potential is V0. Retarding potential is V, negative V. So when we apply potential V there, the potential energy corresponding to that is E times V. Potential energy is charge times potential. So E times V. So with this much potential energy, the electrons are being opposed by the plate A. This is the plate A and this is plate C. Okay. So when we increase the potential, the opposite potential energy also increases. So the speed of photoelectrons also reduces. So at a particular value of opposing potential, that is minus V0, called stopping potential, all the photoelectrons stops because of the opposite potential energy. So at that particular value of retarding potential, the photocurrent becomes 0. So you can see that in the graph here. When the retarding potential applies, stopping potential, the photocurrent reduces, and at a particular value of retarding potential, photocurrent becomes 0, and that value of potential is known as the stopping potential for that particular frequency. When they repeated this experiment with another frequency, we can see that the saturation current is constant, but the stopping potential is different. Here we did the experiment with 3 different frequencies, nu3, nu2 and nu1. Okay. So when the frequency increases, we can see that the stopping potential also increases. That is the second observation. Now in another observation, here you can see that the complete experiment is done with a single frequency nu, but various value of intensities are used. So intensity I1, I2, I3. So at one particular intensity, we can see that the graph that we already discussed. With another intensity, we already learned in the first graph that when the intensity increases, photocurrent also increases. So here also you can see that the intensity increased, the saturation photocurrent increased for I2, then increased current, increased intensity. But on applying the retarding potential, the stopping potential is same for that. So this gives a conclusion that stopping potential depends on frequency. It is independent of intensity. These 2 experimental observations shows that retarding potential depends on frequency and it is independent of the intensity. Now in another experimental observation, they noticed that when the incident radiation frequency is less than a value nu0, no emission is happening there. Therefore no stopping potential is required. So 0 stopping potential there. But when a frequency nu greater than nu0, photoelectron starts emitting from that, and therefore we have to apply some stopping potential also. That is why the graph increases from the value nu0 onwards only. Okay, this is the last experimental observation based on the experimental apparatus shown here. So from all these experimental observations, certain conclusions were made. One is that the photocurrent is directly proportional to intensity. More the intensity of incident radiation, more photocurrent will be there. Second one is that irrespective of the frequency, the saturation photocurrent is same provided the intensity is same. But the stopping potential depends on frequency of incident radiation. More the intensity, more the frequency of incident radiation, more the stopping potential also. And no emission is possible when the incident energy is less than a particular frequency called threshold frequency. When the incident frequency is more than threshold frequency, emission starts. And photoelectric emission is an instantaneous process. That means there is no time lag between the instant of radiation falling on the metal surface and emission of electron. Happens instantaneously without any time lag between these two events. These experimental observations were tried to explain with the help of the theory that was existing at that time, that was the wave theory, the classical wave theory. They tried to explain all these observations with the help of wave theory, but they failed to explain that properly with the help of wave theory. Later, in 1905, Einstein provided a simple explanation based on Planck's quantum hypothesis. According to Einstein, out of the energy of incident radiation, a portion is used to provide work function for ejecting the electron, and whatever energy remains, that will be provided as the kinetic energy of the ejected electrons. That is, whatever energy incident on the metal surface, a portion is utilized for work function and the remaining portion is utilized as kinetic energy of the ejected electron. In mathematical terms, we can write incident energy. If the frequency is nu, then the energy is h nu. Then work function is phi 0 and kinetic energy is half mv square. So h nu is equal to phi 0 plus half mv square. Again, we know that the minimum energy required to eject the electron is called threshold frequency. Minimum frequency is called threshold frequency. Corresponding energy is the work function. So phi 0 is equal to h nu 0. So minimum that energy is required for electron to eject from that. Whatever extra energy is applied by the incident radiation, that will be provided as the kinetic energy of ejected electron. So again continuing, h nu is equal to h nu 0 plus half mv square. Now these electrons, half mv square is the kinetic energy, half mv max square, maximum speeded electrons. So when we apply an opposite potential, that is called stopping potential, that potential energy opposes the kinetic energy. When these two balances, the electron stops and photocurrent stops. That is the mechanism behind the stopping potential. So half mv max square can be replaced by ev0. Okay, so h nu is equal to h nu 0 plus ev0. So ev0 equal to h nu minus h nu 0 or h nu minus phi 0. So v0 equal to, you divide with the e on every time. So v0 equal to h by e times nu minus phi 0 divided by e. This equation resembles that of an equation of a straight line, that is y is equal to mx plus c, where m, the slope of the graph, and intercept c. So comparing this, we can find that slope of such a graph will provide h divided by e, and intercept on the y axis provide, so intercept provide phi 0 divided by e. So when we draw such a graph, the values obtained are as shown here. So these are the explanations given by Einstein. Then Millikan, another scientist, Millikan, tried these experimental explanations of Einstein, and he plotted a graph between frequency and potential, and this is the graph he obtained. We learned from the previous equation that the slope of the graph is equal to h by e. Slope is equal to h by e, and the intercept on y-axis is equal to phi 0 divided by e. W by e is also same. Okay, so hence Millikan calculated the value of h from this graphical observation, and he got the answer for h, the Planck's constant, as 6.62 times 10 to the power negative 34, which is exactly the same value of Planck's constant. So this experimental observation, this experiment by Millikan became a proof for Einstein's explanation of photoelectric emission. Thank you.